Greetings, students. Mr. Munir here. Welcome to your first distance learning lesson. Wow, PreAlgebra. This is great. Love it. Okay, so we are going to be starting with Module 13. Great. What's Module 13 all about? It's about volume. Volume like on a television? Like turn the volume up? No, we're talking about spatial volume, physical reality. And we've got 3 lessons in this module: volume of cylinders, then cones, then spheres. But before we get into these lessons, it's lesson 13.1, let's understand a little bit about what volume is. So let's think about something, okay? Volume, every physical object in the world has volume. But in order to understand what that means, we have to start talking about dimensions. So the first thing we want to talk about is 0, 1, 2, and 3 dimensions. Okay, so what is 0D? 0 dimensions is just a point. Now, even though technically if I zoom in, that point would be really big if I zoomed into it, a mathematical point is different. When we think about a mathematical point, we think about something that has no length, width, or height. It's infinitely small, a tiny little point. So it's actually got no dimension to it. It's just this tiny, tiny, infinitely small point, no length, no width, no height. So that's 0D. Now, nothing exists in reality that is 0D. It's just a mathematical idea, a point. So that's what that is, point. Okay, well, what about 1D? Well, 1D is something that's got one dimension. Well, what's something that has one dimension? Well, that would be a straight line. Now, a straight line, it could be a line segment, it could be a ray, or it could be a line that extends infinitely in both directions. So 1D is a line because notice it can have length, or I can talk about a dimension, one dimension being height. For instance, the height of a teacher or a student is just one dimension. So that would be height. Or width could be the width of a hallway. That's one dimension. So either way, you're only measuring one dimension at a time. That's 1D, and that's just a straight line. You can talk about something being 3 feet long, or someone being 6 feet tall, or a hallway being 10 feet wide. Length, width, and height, all just one dimension. Now, of course, no physical objects actually exist that have only one dimension. If I zoomed into this line, it not only would it have a length, but it would have a height as well. So there's nothing that actually has only one dimension, no physical object. Again, a straight line in 1D is only a mathematical reality. So let's move on to 2D. Now, 2D, what is something that has 2 dimensions? Well, this could be something with length and height, or length and width. But we know something that has 2 dimensions. We see it all the time in PreAlgebra, and that's a coordinate plane. And that's exactly what it is. Something in 2 dimensions, something that has 2 dimensions is called a plane, not an airplane. That's not the type of plane I'm talking about. I'm talking about a plane as a flat surface. So I could fill in all of this with little hatch marks and grids. This could be my x-axis and my y-axis, sure. But a plane is something that's flat. You can imagine a piece of paper has a width and a height, or a width and a length, however you want to think about it. It's got 2 dimensions, okay? That's a flat surface, is a plane. But again, nothing actually exists in 2 dimensions because everything has 3D, 3 dimensions. For instance, even a piece of paper, you might say, oh, it's flat, it's only got a width and a length, but in actuality, you know, it's 8.5 inches wide, 11 inches long, but if you were to measure the thickness of that piece of paper, it's not 0. So it has a 3rd dimension as well, that thickness. So nothing exists in 2D. There's no such thing as a real life plane. Again, it's just a mathematical entity. So let's get to 3D. What's 3D? Well, now we're in the real world, 3 dimensions. Okay, so let's talk about this. We have our plane. We have our plane here. But now I want to add a third dimension to it. How am I going to add a third dimension to it? Well, we're usually used to seeing an XY axis, but I could also create a third axis as well. And if you imagine this axis coming out of the page, if this is X and this is Y, then this would be my Z axis. That would be my third dimension. And this could be the width, the height, and the length of an object. Now, what's a simple object that I could draw in 3 dimensions? That would be a cube. And I'll do my best to draw a cube here, freehand. Let's see how I do. Not too bad. Let's get rid of that one. Okay, so 3D, cube. Now, a three-dimensional object can be anything. It's not a point, it's not a line, it's not a plane, it's a three-dimensional object. Now, a three-dimensional object could be anything. My physical body is a three-dimensional object. The computer I'm working on is a three-dimensional object. A cube, a cone, a cylinder. The entire building that I'm in right now, our school, is a three-dimensional object. So when we talk about three-dimensional objects, it's not so simple as saying, oh, it's a 3D, what's the name of it? Like in 0D, it's a point. In 1D, it's a line. In 2D, it's a plane. In 3D, well, the question is, what type of three-dimensional object is it? And that's where we get into volume. That's when we get into these different physical objects. And where we go from there is up to us. Now, of course, there are going to be simple objects like a cube or a cone or a cylinder or a prism or a pyramid. They're going to be simple objects and it's going to be simple to find their volume. And then there are also complex objects. For instance, this robot. This is a physical object in 3 dimensions, but if I'm going to try and find the volume of this robot with math, it's not going to be that easy. Well, fortunately, we don't start with crazy complex objects. We start with very simple objects, and that's what we're going to be learning about in this module. So now let's take a look. Let's take a look at just some preview stuff before we get into something, before we get into volume specifically. In order to understand volume, we have to understand beyond length, which I think is a simple thing to understand, we have to understand area. Okay, so what is area? Well, a simple thing to get is like the area of a rectangle, base times height. So if I have this rectangle and the base is 3 and the height is 2, well, I could separate that into unit squares, and each one of these squares has an area of 1. Well, so the area of that rectangle is going to be the base times the height, which is 3 times 2, or 6. Okay, this is elementary stuff. You get that. All right, but what about a circle? We understand area. Oh, that was a really, really bad circle. Let's see if I can use my tools here to make it a little bit better. That looks a little better, right? Nice. Okay. That's kind of cheating, but you know, that's what tools are for, right? All right. So I've got my nice circle. Let's put a chord across it and through the center. And a chord on a circle is a line that goes from one part of the circumference. The circumference is that the entire outer edge of a circle. So a chord goes from one point of the circumference to the other point. So that's a chord, but specifically if it goes through the center of the circle, I call this a diameter. So the diameter of the circle is the width from one point of the circumference to the other point of the circumference that goes through the center. So the length of that chord. Okay, that's the diameter. Now half of that diameter, so this from here to here, is the radius. Okay, so radius equals diameter d over 2, or in other words, diameter equals 2 times the radius. All right, cool. So once I know this about circles, the next question is, how do I find the area of a circle? Well, the area of a circle can be found by doing pi r squared. So the area of a circle is pi r squared, and we know pi, that's a good friend, and we can approximate it with 3.14 or 22 over 7. Both of those are good approximations. Let's use 3.14. So it would be 3.14 multiplied by whatever the radius is squared. So let's say the radius of this is 3. Then the radius would be 3.14 times 3 squared, or 3.14 times 9. Okay, if I use my handy dandy calculator here, 3.14 times 9 is about 28.26. So the area of this circle is going to be 28.26. Now, I haven't talked at all about units, but if I say that this is 3 inches, then the area is always going to be in units squared. So I would say the area of that would be 28.26 square inches, or 28.26 inches squared. Both of those are appropriate. So that's it. That's how you find the area of a circle. So area of a rectangle is easy. Area of a circle, a little bit more challenging. I would go into area of triangle. Let's just go into it just to be make sure we're dotting all our I's and crossing our T's. An area of a triangle, here's the base, here's the height. Well, the area of a triangle is easy if you think about it as half of a rectangle. The area of a rectangle would be base times height. But wait a second, if I eliminate that half, well, I'm just left with half of that rectangle. So the area of a triangle is 1/2 base times height. So if this base was 4 and the height was 6, the area of that triangle would be 1/2 4 times 6, which is 1/2 of 24, which is 12. And again, if it was in inches, it would be inches squared. Cool. All right, we understand area, but now what about volume? How does that work specifically? Well, in order to help you with this, let's take a look at this on GeoGebra. Okay, so we're used to seeing unit squares with area, but what about unit volume? Okay, well, here we go. We have a cube here, and this cube has a volume of 1. If each of these lengths was 1 inch, then it would be 1 inch by 1 inch by 1 inch, which would be 1 times 1 times 1 is 1 cubic inch. Cool, interesting. Area, it's squares, square inches. Volume, it's cubes, cubic inches. Math vocabulary. So this is a unit volume. So this cube has a volume of 1. Okay, 1 cubic inch, let's say. Well, what about if I extend this out a little bit now? Instead of it just being 1 cube, now my shape is 2 cubes put together. Well, now it's got a volume of 2 cubic inches because I have 2 cubes. Cool. Awesome. And if I think about the dimensions, this would be 2 times 1 times 1. So to find the volume of a rectangular prism, this is called, we would take the one dimension, multiply by another, and multiply by another. If I call this the length, it'd be the length times the width times the height. So this would be 2 times 1 is 2, times 1 again is 2. So the volume of this is 2. All right, cool. Well, what about now if I give it a different width and make my width 3? Well, now count them. I've got 1, 2, 3, 4, 5, 6 cubes. So it's 2 cubes wide, 3 cubes long, and 1 cube high. So my volume now is 2 times 3 is 6 times 1 is still 6. Cool, I've got 6 cubes, and base times width times height, or length times width times height, I've got 2 times 3 times 1 is 6. So it makes sense. All right, well, now what happens if I change my height? Now, it's a little harder to see now. It's a little harder to count all the cubes, but if I wanted to, I could. Remember, this yellow layer has 6. And how many layers do I have now? I have 1, 2, 3, 4. So if I have 6 in each layer and I have 4 layers, it's 6 times 4 is 24. Cool. So I can figure out there are 24 cubes in this shape, which again is a rectangular prism. But what if I wanted to find the height just by using my formula? Okay, well, let's actually write down the formula now so you can see it. All right, if I've got a rectangular prism like this, boom, 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 then I've got my length, my width, and my height. Cool. Well, the volume of that is length times width times height. So in our case, what do we have on our GeoGebra setup here? Well, let's take a look. I'm going to bring this in. Well, our length here is 2, our width is 3, and our height is 4. So the volume is 2 times 3 times 4, or 6 times 4. 2 times 3 is 6, times 4 is 24. And again, if this was all inches, 2 inches, 3 inches, and 4 inches, then the volume would be 24 cubic inches. Cool. Now with this, I think you can have a pretty intuitive understanding of what volume is. It's the amount of three-dimensional space that an object takes up. Okay? So if I say something takes up 24 cubic inches of three-dimensional space, that means the volume of that object is 24 cubic inches. Cool. All right, the bigger a volume, the bigger the object. It's pretty straightforward. Now, a rectangular prism is pretty much the most simple object that we can calculate the volume for. Beyond that, we can go to pyramids, cylinders, cones, all sorts of different prisms. There's all sorts of different objects that we can have mathematical formula to calculate their volumes. And it's pretty cool because math gives us the ability to do this. This is real world stuff. This is giving us the ability to figure out volume. Awesome. And we can do it with simple equations. We just saw it for a rectangular prism. Well, now that we have that, we can get started with our understanding of volume of cylinders. So let's go ahead and get into it, shall we? So if you're following along in your book, go ahead and open up to lesson 13.1. Now, modeling the volume of a cylinder. How do we do this? Well, if you follow along with the book, it says, hey, put a bunch of cubes in there and then add them up and stack them up and see how many stacks of cubes there are going to be. Okay, well, that's one way to do it. But let's go back to our GeoGebra example and let's take a look at this, okay? I'm going to bring my height back down to 1. Now, if I just look at this, right? If I'm calculating the volume of this first layer, it's actually the exact same thing as calculating the area of that face, okay? If I had a rectangle and I wanted to find its area, it would just be 2 times 3. It would be base times height, right? So here, the area of this rectangle is just 2 times 3. 2 times 3 is 6. Cool. Well, that also happens to be the volume of this layer. So I then, when I make my height bigger, I take that same volume, which was 6, and I multiply it by the amount of layers, which was 4. So 6 times 4 gave us 24. But what if we think about it in a different way? What if we think about it in terms of the area being multiplied, the area of the base being multiplied by the height? Well, then it becomes pretty obvious how we find the volume of any kind of prism. Well, let's take a look. For this, in this case, the area of the base of this prism is 2 times 3. 2 times 3 is 6. That's the area of the base. If I multiply that by the height, which is 4, I get 6 times 4 is 24, which is the exact same answer I got by counting the cubes. Okay, well, how can I extend this to something different? Well, let's think about it in terms of a different kind of prism. For instance, let's think about it in terms of, this one's a little bit harder to draw, so I'm going to do my best, triangular prism. So you can imagine you've got two triangles. Boom, there's my 3D object. And this would technically be a hatched face because you wouldn't be able to see it. But let's say my triangle has got a base of, has got a base of 4 and a height of 6, let's say. Cool. And let's give it a length of 8. All right. And this is a right triangle, so it makes it easier for us to get the area of that triangle. Okay. Well, now in this case, I don't have a bunch of cubes that I'm adding up, but let's use the same process that I used for the rectangular prism, where the volume, it's not just length times width times height, it's actually the area of the base times the length of the prism. Okay, so bringing back my GeoGebra example, this would be considered the area of the base. Here's my base here. And this was 2 and this was 3. And then this is my prism, the length of my prism. This dimension is the length of my prism, which is 4. So the area of the base is 2 times 3, and the length of the prism is 4. So for this example, the area of the base is 2 times 3, and the length of the prism is 4. So 2 times 3 is 6, times 4 is 24. Cool. Good. But what about for a triangular prism? Well, in this case, the area of the base, well, what's the base of the prism? The base of the prism is the face that is extended or extruded out in 3 dimensions. So I've got a triangular prism here. The base is that triangle, and the top of it is the other triangle on the other side of the prism. So what's the area of the base? Well, remember our formula for the area of triangles? It's 1/2 times the base, which is 4, times the height, which is 6. But what's the length of our prism? Well, that's our length right there, is 8. So to get the volume of our triangular prism, which is what that is, it's 1/2 times 4 is 2, times 6 is 12, times 8. 12 times 8 is 96. And again, if this was all in inches, this would be inches cubed. Cool. That's how you find the volume of any prism. You might say to me, well, what if the prism has a base that's not a rectangle, like in this case, or a triangle, like in this case? What if it's a pentagon or some crazy polygon with 87 sides? Well, you do the exact same thing. You find the area of the base and multiply it by the length of the prism. It's as simple as that. Then you say to me, well, Mr. Manier, this is all nice and good, but what does this have to do with our lesson? I thought we were finding the volume of cylinders. Cylinder isn't a prism. It's a circular circle with the thing. Wait a second. Let's take a look at a cylinder. Before we actually take a look at a cylinder, let's look at polygons. Well, a 3-sided regular polygon is an equilateral triangle. Remember, regular means that it's got all the same interior angles and lengths of the sides. So equiangular, equilateral, okay? Equal angles, equal sides. A 4-sided regular polygon is a square. What about a 5-sided? Can you guess? What is it called? That's a pentagon. And what about a 6-sided regular polygon? Well, that's a hexagon. Cool. And an 8-sided, easier to draw than a 7-sided, so please forgive me. An 8-sided regular polygon is a stop sign. Just kidding. It's an octagon. Well, if I keep drawing more and more sides, eventually I'm going to get to a shape. Let's say this is, 10 sides. That was really sloppy, but who cares? Eventually I'm going to get to a shape that looks remarkably like a circle. Let's say this is a circle. It's pretty close. A circle, in a lot of ways, is an infinitely sided regular polygon. So a regular polygon with an infinite amount of sides, the more sides you add to a polygon, the closer it approximates a circle. So in a sense, a cylinder is a circular prism. It's not a rectangular prism because the base is in a rectangle. It's not a triangular prism because the base is in a triangle. It's a circular prism because the base is a circle. So let's take a look at a cylinder in our book. So here's a good one. That's a nice looking cylinder. I like this cylinder. It's a good one. I like its dimensions. It just makes me happy looking at this cylinder. Okay, so the radius of the cylinder, boom, the base of the cylinder is a circle. The length is 10. If I were to call this a circular prism, the area of the base would be the area of the circle, and the length would be 10. Cool. Huh. We don't call it a circular prism, we call it a cylinder. So that's the last time I'm going to call it a circular prism, but we're going to use the same formula for the volume of a cylinder as we do for the volume of a prism. It's the area of the base times the height, or the length of the prism. So, how do I find the area of the base of a cylinder? Well, that's just the area of a circle. And remember, if you look at this, yeah, that does look a lot like a prism, except instead of the base being a square or a rectangle or a triangle, the base is a circle. Cool, so I can use the same formula. Well, what's the area of the base of a cylinder? Well, the base of a cylinder is a circle, so I'm talking about the area of a circle, which is pi r squared. What? Well, that's so simple. To find the volume of a cylinder, you just do pi r squared times the length or the height of the cylinder. It's really that simple. Okay, well, let's do it. Pi, what's the radius? 3 squared times the height, 10. Cool. So it's pi times 9 times 10, which is 90 pi. Now, depending upon the situation, okay, remember, first off, before I go into that, I got to make that inches cubed, keep my units. Depending on the situation, you might want to keep it as 90 pi, or you might want to use your awesome math brains to multiply it in your head, or you might just want to use a calculator, depending upon the situation again, to get a good approximation of 90 times pi, and you would get 282.7. So this is approximately 282.7 inches cubed. That's the volume of the cylinder. Remember, I said approximately because we can only get an approximation of pi. This is the exact answer. The volume is exactly 90 pi inches cubed, or approximately 282.7 inches cubed. That's it. That's how you find the volume of a cylinder. It's really that simple. Okay. Now, so you can see in the book that they use 3.14, which is why they got 282.6. That's obviously the danger of using 3.14, but notice they tell you 3.14, they tell you to use 3.14 as an approximation for pi. So depending upon what you use as an approximation for pi, you're going to get potentially a different answer depending upon your dimensions. Okay, so there you go. That's it for that one. Then they do the same thing for this one, except they give you the diameter. Uh-oh, be careful. They don't give you the radius. They give you the diameter, 6.4 centimeters. So to get the radius, you just divide that by 2. If the diameter is 6.4, then the radius is half of that. 6.4 divided by 2 is 3.2 centimeters. Once you have that, plug it into your formula. Pi times r, which is 3.2 squared, times the height, 13. Sweet. And they get approximately 418 centimeters. Okay, cool. Nicely done. Let's move on. Number 4 and number 5. We can work these out. I'm going to go ahead and work out number 4. Let's make sure we're being comprehensive in our approach. All right, volume of this cylinder. You could just say V. You don't have to say volume cylinder with that subscript. I like to do that because it reminds me of what I'm doing. Is again the area of the base times the height of the cylinder. But you know what? I don't have to do that every time. I can just say it's pi r squared times h. That is the formula for the volume of a cylinder. Well, that'd be nice if I had the radius, but I don't. The radius is the diameter over 2. I've got the diameter is 10 inches. 10 inches divided by 2 is, of course, 5 inches. So now that I've got my radius, pi 5 squared times height is 6 is pi times 5 squared is 25 times 6 equals 25 times 6 is 150. Oh my goodness, 150 pi inches cubed. Awesome. Then I'm going to go ahead and calculate 150 times pi or 3.14, whichever one you want or are told to use. I'm going to say that's 471.2 approximately. 471.2 inches cubed would be the volume of that cylinder. Awesome. You could do 5, very similar. Okay, real world context. Big Bertha has a diameter of 8 feet and is 4.5 feet deep. By that they mean the height of the cylinder or the length of the cylinder, depth. It's all the same. You're going to have a circle and then you're going to have a dimension of length or height or depth. They're going to call it whatever they want to call it, but the key is understanding the difference between diameter or radius and depth or height or width. If they're talking about diameter or radius, they're talking about a dimension of the circle, which is the base of the cylinder. And if they're saying depth or width or height or length, then they're talking about that length dimension, okay, of the cylinder. All right, so first you want to find the radius, which is 8 over 2, which is 4. You've got that the depth is 4.5, so that's the h, the height in this case. So it's pi times 4 squared times the height, which is 4.5. Calculate, simplify, they keep using 3.14, awesome. A drum company advertises a snare drum. This is now your turn. A drum company advertises a snare drum that's 4 inches high and 12 inches in diameter. That is literally the exact same problem. Except instead of saying depth, they've said it's now 4 inches high. Okay, it's the same thing. You do it in the exact same way. Cool. And that's pretty much it. Once we've got into guided practice, we know that we've learned everything that we need to know in this lesson. So taking a look at the independent practice, this is basically what your homework is on myarchrw.com. Those assignments, those homework assignments on there, that's the independent practice. So we can see that it's basically the exact same deal. And then you've got some word problems. Okay, but let me challenge you for a second. Let me challenge you. Let's see, what's my time looking like here? Where am I at? 33. Real quick, I'm just going to challenge you. I'm at 33 minutes, so I don't want to challenge you too hard. Let's say I've got a cylinder, and I say that the volume of the cylinder is, let's say it's 20 pi. I keep it in pi, inches cubed. And I tell you that the radius of that circle on the base, that radius is 2 inches. And then I ask you to find the height. Well, how could I do this? Well, I know that the volume, if I want to find the height of the cylinder, I've got the volume and I've got the radius, but I don't have the height. Well, I got to go back to my formula. V equals pi r squared times h. Well, I know my volume this time. It's 20 pi inches cubed. Equals pi r, I know my radius, is 2 squared times my height. I don't know my height. Well, let's see if I can simplify. 20 pi equals pi times 2 squared is 4, so 4 pi times h. Well, let's go ahead and get rid of some terms. The first thing I can get rid of is my pi, right? I've got a pi on both sides, so I can get rid of that. And I get 20 equals 4 times h. Well, now I can divide both sides by 4, and I get h equals 5. Sweet. 5 inches. I figured it out. Now, I'm not going to go into this one, but for all you brilliant young mathematicians out there, what if I gave you the height but didn't give you the radius? So I've given you the volume and I've given you the height, but I didn't give you the radius. How could you solve that problem? I'll leave that one up to you. Well, that's it for me today. Until next time, Godspeed and enjoy your maths.